In this video, we are going to look at the atomic emission spectrum and some of the quantum stuff from chapter 5.3. So be able to explain what is the atomic emission spectrum, define Planck's constant, the photoelectric effect, photon, ground state, and the Heisenberg uncertainty principle. Be able to relate the absorption and emission of energy to electron levels, define the photoelectric effect in terms of solar panels and electronics. An atomic emission spectrum is when you pass electricity through a gaseous substance and you get visible wavelengths of light out of it. This will be different for each substance, and that is the atomic emission spectrum of that substance. What's really happening here is you're exciting electrons and they drop to a lower quantum level. Remember Bohr's model of an atom. The energy that is emitted when they drop to that lower energy level is going to be given off as light. Which energy levels you see is going to be due to which types of drops those electrons are doing. So a higher drop is going to get a higher energy wavelength of light. This also is why different elements give off different types of light. So if you had hydrogen here, you see it's kind of purple. That's because it has some blue wavelengths and a red wavelength. Neon, it's that classic kind of orange color, many yellow wavelengths there, and argon has a more blue spectrum. You may also notice this in sodium lamps, which give off an orange glow, or mercury lamps, which give off kind of a blue glow. Now, I mentioned in there that you have a different wavelength of light, and that is going to have a different energy level. This is because different wavelengths have different energy. Well, how do we know what wavelength has what energy? What we're doing here is we're going to use Planck's constant to actually determine how much energy a wavelength of light has. Remember how you had that metal that glowed first red, then yellow, then white? The white had higher energy than the yellow, which had higher energy than the red. This is because different wavelengths give off different amounts of energy. So what happens here with this equation is that you have the amount of energy, E, is equal to H, which is Planck's constant, 6.63 times 10 to the negative fourth joules per second, multiplied by V, which is the frequency of that light. As the wavelength decreases, your frequency is going to increase, which means the energy is going to increase. So blue light has more energy than yellow light. Einstein used this idea that different wavelengths of light have different amounts of energy to explain the photoelectric effect. What happens is if you shine red light on a substance, it will not necessarily give off electrons. Like if you shine it on potassium, potassium will not have any excited electrons. But chemists found that if you shone yellow light or blue light on that same potassium, you're going to get some electrons excited off, essentially an electric charge. And this could not be explained until Einstein theorized that something called the photoelectric effect is because this electrons are ejected when light is going to be shown on a metal because that light has energy. And not only that, but there is a distinct amount of energy per unit of light because the electrons will be given off under weak yellow light, not strong red light. And more electrons will be given off if you have more light. So the brighter the light, the more electrons are going to come off. Classical physics could not really explain this, but Einstein explained this in terms of something called photons. A photon is a single quantum of light, so a measurable small bit of light. Oh, it's a measurable small thing. Is it a particle? Well, yes and no. The quanta of light are called photons, and that's because light can behave both as a particle and as a wave. We can measure the frequency and wavelength of light, wave, or we can measure it in distinct quantized quantities, i.e., photons. And this can also be used to explain some more about the Bohr model. So you see, if you have electrons coming down from different energy levels, they were giving off discrete amounts of energy. Discrete meaning this distinct. So you could have an electron drop down from excited state number 6 all the way to n equals 2. So going down from energy level 6 to 2, and then you're going to have a wavelength of light given off that's purple, which is 410 nanometers and has a certain given amount of energy. These are all going up when energy is absorbed and are dropping back down to the ground state, which is the lowest possible energy an electron can have. The electrons at higher levels give off more energy, i.e. shorter wavelengths of light. So what wavelengths of light can be emitted when an electron goes to an excited level and then back to the ground state depend on where the electrons are in an atom, which depends on which electrons are filled. So you can kind of see how this relates to the rest of this chapter. Now, one more fun thing is that when you see an electron, it's because you know what position it was on. So a photon of light comes in, hits an electron, and you see a reflected photon in the microscope. This reflected photon tells you where it was. So the velocity by this point has changed because of the interaction of the photon and the electron. This is why the Heisenberg uncertainty principle states you can know where an electron is, or you can know its velocity, but you cannot know both.